Good afternoon, everybody. My name is Edgar de los Santos. I am part of the technical support team at MySIT in the US office. If you can hear me, can you please press the button with the hand? Thank you very much. Today we're gonna have the second session from the training series on the substructure analysis and design. We had the first session that was focused on the only substructure analysis and design. We separated the substructure from the superstructure and went over the different parts of and modeling features in the program. In today's session, we're going to combine the superstructure and the substructure as an all-in-one model. And in the following session, which is in about 2 weeks, we're gonna have the essential soil structure interaction for bridges. In this case, we're going to have the superstructure and the substructure, and also we're gonna implement the soil properties using point spring supports and the different functions that are available in the program. So for today's content, we're gonna present MyDaCivil, which is our structure analysis program for bridges. We're gonna also go over the advantages of having a full model, which means the entire structure modeled in one platform. Also, we're going to go over the modeling functions in MyDaCivil using the superstructure and the substructure interaction, and also the different boundary conditions. With the boundaries, we can model the bearings, we can model the soil properties, and so on. Also, we're gonna go over the design features. In this presentation, we're going to use only concrete. We're gonna go over the pre-stressed concrete and also the reinforced concrete design functions that we have in the program. So MyDaCivil. For you guys, the people that don't know the program, MyDaCivil is an all-in-one solution. You can model, analyze, and design all types of bridges, as you can see here, from the most basic one, which is a slab bridge, to the suspension bridge, which is one of the more complex ones. We can also perform different types of analyses, whether it is dynamic analysis, static analysis, and so on. Moving load analysis, so it's up to you. You have the different types of analysis available for the design of a bridge, in this case. So going over the different advantages of having the full model, and by full model I mean having the superstructure and the substructure together in the same platform. The first and main advantage is that we can obtain more accurate results using the two parts of the structure. If you model the entire structure, as you know, it works together. The entire structure itself works together, which means that the behavior of the superstructure influences the substructure and vice versa. So by separating them, we are not really creating the real or trying to model the real behavior of the structure. So separating them, we obtain different values from reality, or farther from reality, because we're simulating things using the programs. We can approach the most real behavior using a program, but in the case that we separate them, then we're really off by relatively a lot. In the case of, for example, seismic analysis, the period of the structure is influenced by the stiffness and the geometry of the structure and so on. So if we take out part of the substructure, let's say piers, that's gonna influence the behavior of the bridge, and for seismic analysis as well. So it's better if we have more accurate results by putting the superstructure and substructure together. Another good thing is or advantage is that you don't need multiple files. Nowadays, for a bridge we have 4, 5, 6 different models that we have to transfer from, the loads, the results, and so on. So in this case, the most important thing is that you're gonna have everything in the same platform. You're just gonna need to learn one program, and you don't have to transfer data from one program to another. Everything is there, and you'll be able to obtain all the results from just one model. The other good thing or advantage is that you're gonna spend less time modeling. Uh, Imagine you have three different programs that you have to transfer the loads from one to another. Some companies have that system very well, um, the logistics very well, but let's say that you don't have such a good system where you transfer everything is kind of manual. You're gonna spend a lot of time transferring the information from one program to another. Another thing is that some parameters are not assumed. As we went over the first session, there are many things that you assume when you split the superstructure from the substructure. Where if you don't have the superstructure, you just put in some type of reaction over the bearings, and that will be it for your substructure analysis and design. Um, if you have, let's say, if you take out part of the substructure, then you don't know how much the bottom part of your structure is gonna deflect, or the behavior of it, and so on. So in order to have a more realistic parameter behavior, we have to model the entire thing using the finite element program. And the most important thing is that we're gonna obtain more economical designs. Nowadays we have different codes that only allowed us to perform so much or to obtain so much from the materials. But in the case that we have a more conservative design, then that gives us more economical, less economical projects. So in the case that we have the entire model, we can obtain more accurate results, which gives us less conservative um, results, and then from there we can obtain a more economical design, which is at the end, in our industry, money and time are very, very important things. Now, going into the modeling itself using the program, let's talk a little bit about the piers and abutments and bearings, which are the one of the three main things on the substructure. As I mentioned in the last presentation, piers and abutments are an integral part of the load path between the superstructure and the foundation. So their main functions are to transfer the load from the superstructure, the vertical loads, and also receive the horizontal forces on the bridge. In addition, the abutments also are used at the ends of the bridge to retain the embankment. Here we have an image of a kind of cool bridge, which has different types of piers and also the abutments there. Just to show you, just an overall intro on the parts of the substructure. In this case, what we're going to do is we're going to model the superstructure and the substructure in the program using Wizard that we implemented recently in the program. The Wizard is a composite girder, and it's an entire module where you can perform the modeling of a steel composite bridge or the pre-stressed composite bridge. We have implemented these two. These were the two last functions that were implemented in the program. Right now, the program can absolutely do any type of bridge. We generated the wizard just to improve your experience with the program and model it easier. You're gonna see how easy it is to model using the program, and from there you can get the report generation using for the design and load rating checks as per ASHTO. You can do it for RC, steel composite, or pre-stressed composite, and also we're implementing the Canada code this year. So, going into the composite girder, pre-stressed concrete in this case, this is how it looks like. It's a dialog box that looks like this one, that has different tabs. In this case, it has 5, and each tabs represent each part of the bridge, where it is the layout, whether you have a curved bridge, or the sections, and so on. So now I'm going to introduce the different functions, and then we're gonna use the composite girder in the program so that you guys can know or have an idea of how it is done. So for the layout tab, we have different functions in the program. We have a diagram that shows you the different parts of the definitions that are at the bottom here. So in the program, you can perform precast or splice girder automatically using the wizard. And also, the program has many types of modeling features. Whether you want to use all frame, in which the program generates all the members using frame elements, in this case beams, or you have the girder as frame and the deck as a plate. It's up to you how you want to decide how is the model generated using the finite element. So you can choose here which type of modeling do you want to have. You can insert here the span information, the span length, the curvature, whether you have a radius, the type of radius that you're having. Also, one of the important features is the substructure. You can model or not the substructure. In this case, we're going to model it so you can have an idea of how it is done in the program. And here you have the different types of, elements, the sections that you're gonna input for the substructure also. Then we have the section tab. In here we can define the materials for the sections that we're using. Also the sections that we're gonna use for each span, and the number of girders that we're gonna use. Also the diaphragm distribution that we're gonna assign to the bridge. So from here we can jump into the tendon tab, which is one of the most important one that we have implemented. Here you have different types of tendons that you can implement in the bridge, where you have your own layout of the tendon, or you can use the type of wizard for generating the tendons, and the program gives you the steps to perform that type of tendon layout. We have different tendon types. We have straight, hard, curved tendons. You can define that using a table also, where you can define the number of tendons, the distribution, the displacement, and the vertical direction. You can also define as many tendons as you want. And you have the table, which is this one, that shows you the exact position of each one of the tendons, which is kind of great, so you can see it before you perform it. Then we have the load tab. In the load tab, you can define the different types of loading, whether you have the barriers, the jersey, you have the option of, with the diagram, defining what is the width of each one of the parts, the barriers, and so on. And then we have the definition of the dead loads. Here you can define the DC and DW before composite and after composite. As you know, our codes requires us to define or to check the deformations, whether it is the pre-composite or the composite section. So you can define the different loadings here, and then from there you can check the deformations of each one of the parts. In this tab, we also can define the moving load analysis. So for this case, let's say that we want to implement the ASHTO LRFD. In the program, we can do that using the wizard. I'm gonna show you how it is done and how you can select the truck that you want to use. Then we have one of the important things, and which will probably take you more time generating, it's the construction stage analysis. The program can do it automatically, and here you can establish the construction sequence of the bridge and see the behavior in short and long term. You can consider the effect of the tendons, in this case for pre-stress, and also what is the behavior of the bridge pre-composite and after composite. This is the model that we're gonna do today, and we're gonna open my Civil to show you how it is done in the program. Alright, so this is my Civil. For those of you who don't know the program, this is our graphical user interface. In the tab we have the ribbon menu. It's very similar to AutoCAD. So you can here define, as per each tab, the program gives you the specific functions for each tab. For example, let's say properties. Here you can define the material properties, and you can define them here, or the section properties on this particular dialog box. For materials, we have already defined different types of materials, but in the program you can do steel, concrete, steel reinforced concrete, or the user defined. So the program is very open to whatever you want to model, as you can see. In this case, we have ASTM. Also, we have Canadian code as per standards for the material database. So you can from here define the material properties in your model. Also, we have section properties, and we have defined them here. But let me just go over the ribbon a little bit. You have the load tab. You can define the static load cases, dynamic moving load, etc. And the way the program works is from left to right. So let's say you want to define a load, you define the static load case, you define the static load cases, and then you go from left to right. Static load cases, and then here you can define the different loading. So that's how more or less how it works in the program. We also have something called tree menu. In this case, we have the tables tab, in where you can obtain the different properties of the model using the tables. So let's say that you have different model nodes generated in the program. From here you can obtain a table which you can export to Excel and so on. We also have the worktree. In this case, I have defined different materials and sections for this model. We're not going to go over the modeling itself of those particular parts, but here you can see that you can define different types of material of sections. In this case, you can define typical sections from ASTM, solid sections. You can also define SRC sections, as you can see here. You can also do combined sections, these ones. You can also define PSC, which in this case is the one that we're using. We have different PSC sections in the database, and you can also do the sections as per different DOTs. We have worked with different DOTs in the US, and we're implementing them as we become more familiar with them, but we are in the process of implementing every DOT in the US. Also, we have taper sections, combined sections, as you can see here, and also a steel girder. In this case, I have defined different sections. Let me just show you so you can have an idea which one of them. These are the ones that we're going to use for this model. And then we also define the properties of the tendons. In the program, you can do internal, pre-tension, post-tension, and external tendons. So the program can basically handle any type of tendons. So in the groups tab here, the groups are used for the generating the construction staging. So in this case, you can activate or deactivate different parts. The wizard is gonna do that automatically, but just keep in mind that this is used for that. And then we have the report tab, where you can do the report generation. We have you can save images, copy and paste, and so on. Define tables and then use them in the Word document in the program. We have here also something called the task pane. In the task pane, we have another function. Let me just show you. We have something called the task pane. So for the task pane, we have implemented the particular function that shows you where is the location, or what are the steps that you need to take. So let me just import a user defined one. We have this available for you users. So we have generated this function that tells you the steps that you need to take. So let's say you want to define the unit system, the program automatically does that. You want to use the wizard, which is under the structure function. You can just open it here, and then the program is gonna automatically open it. And then you can have the verified and temporary results here. and then design functions. On the right side of the program, you have the different views, and then at the bottom you have the units. So let me just open a wizard that I have established. This is the wizard for the program. Let me just open it up. And here we have the layout tab. As I mentioned, you can define where it is a splice, girder, or precast, everything as frame on the modeling, or the deck as plate, and the girders as frames. Here you can define the span information, the length of each one of the spans, where you have a radius, the length of the radius. You can also define the substructure and the superstructure, and here you can define the links or connection between the superstructure and the substructure. Those are the bearings. We're gonna go over a little bit about the bearings of the bridge and how you can model them. But here the program can do that automatically using this wizard. You can also define the height of the columns and the pier caps, and you can also define the type of bearings that you're using. In this case, you can define the stiffness in each direction of the bearings. So depending on the type of bearing that you're using, as I mentioned in the previous session, you can define the stiffness in each one of the directions using the wizard. In this case, you can also define the pier sections and materials, and the length and height of the pier cap and column. Then we have the section tab. Here you can define the thickness of the deck, the number of girders. You can also go and use the guide to you can refer to the guide and then see from there what the program is asking you. As you can see, the wizard works really well with you, in the sense that it gives you guides for each one of the parameters that the program is using or asking. Here you can define the diagram section and the spacing of the diaphragms, whether it's per distance or divisions per span. You can define it here. You can also generate the 10-point element as required by the code, and you can define the section for each one of the spans. Then we have the tendon tab. Here you can define the layout or the assignment on the table. So let's say you have a curved tendon. You can define here the curvature of the tendons using this guide as reference. You can tell the program where is the tendon going to be assigned, the reference sign, and here you can define whether it is a straight, arced, curved, and the number of tendons that you're having, the tendon property, and then from there you can get the table. But this is more or less how you can define it in the program. Then we have the load tab. Here you can define as I mentioned, the width of each one of the barriers, also the magnitude of the density of the concrete, the thickness of the deck. You can also define the after composite parts with the variant median strip with the wearing surface, and here you can define the moving load. In this case, I'm gonna use the Ashton RFD moving load. The live load option activates automatically, and then from here I can define the traffic lanes. In this case, I'm gonna define just one lane just to show you, and I'm gonna assign it at 20 feet from the left side of the bridge. Then I'm gonna define the vehicles. The program has standard vehicles with different codes. As I mentioned, we're working with DOT, so we have the legal truck, the permit trucks, and the vehicles for each one of the DOTs. We work with Louisiana, Illinois, Rhode Island, Ohio, and so on. But in this case, I'm just gonna use the actual RFD, and I'm gonna use the HL93. We have the HL93 in the program. We also have the fatigue truck and the tandem truck. And here I'm defining the dynamic allowance, and the program automatically loads the truck right here. I close it here, and then we go into the construction staging. So in the construction stage, we have the construction stage sequence. We can also use the guide, as you see here, and we can select whether or not we want to use to perform the construction staging in the program. So in this case, the stage 1, the erect substructure and install the false work. Stage 2, erect the precast segments, cast splices, and make it continuous, and then perform the first post tensioning, second post tensioning, and then remove the temporary supports. That's more or less how it is here, or predefined. Here you can define the duration of each one of the days that you want to use. In this case, we're not gonna assign the construction stage, just to save some time, and just focus a little bit more on the substructure part. You also have the function for defining the reinforcement. So here you can define the reinforcement for the girders. So where you want to define reinforcement, here you can tell the program how many rebars do you want, the diameter of the rebars that you're using, and so on from there. And the program can take that into consideration for the design as well. So let me just click OK, and then with that, the program is going to generate the entire bridge in no time. That's it. So let me just uncheck the nodes and see what's assigned into the model. Here in the tree menu, I can see what is assigned into the model. I use it all the time. Since I'm part of the technical support, I can check what your models have and what you guys did when you send it to us. So from here we have different types of links. In this case, we have rigid links that are connecting the superstructure with the substructure, and also we have elastic links, which are the bearings that have the stiffness that we define in the wizard. We also have the groups. As I mentioned, the program generates the groups automatically, and you can see here each one of the groups that are being assigned in the model. Also, from here we have defined the traffic lane. As I mentioned, it's 20 feet from the left portion of the bridge. You can see it here, but in this case I'm going to the load tab and define the moving load case for the moving load analysis. So I'm gonna add the moving load case. You can define the multiple presence factor automatically here, but in this case I'm just gonna do the one lane as I defined it, minimum and maximum number of lanes assigned, and I'm just gonna select one of them. That's my moving load case. You can have as many moving load lanes or vehicles as you want. In this case, I'm just gonna go over the just go back to the presentation and show you the different types of bearings that we have available. So for the bridge bearings, just going over a little bit, the function of the bearings is basically to transform the forces from the superstructure to the substructure. It also provides the rotational or translational restraints in each direction, and you can define them in the program with a particular stiffness. They're used to accommodate the deformations due to the thermal expansion or contraction, the elastic deformation under life load, the seismic forces, creep shrinkage of the concrete, also the wind loading, longitudinal forces such as the braking force, the settlements on the supports, and so on. These are very important guys that work in the bridge, and we for that reason have to consider them in the model. So how we can consider them in MIDAS Civil? MIDAS Civil, the bearings are defined using different types of boundary conditions. So in the program, we can define supports, point springs, surface springs, links. For example, you have nodal boundary conditions that restrain different degrees of freedom. For example, let's say we have the support. Support will constrain the degrees of freedom in each one of the direction, rotational and translational. We also have elastic boundary elements, which are the point spring supports. We're going to talk about them in the following session, where we can define the soil properties using these point spring supports. Then we have the elastic links that we use to model the bearings with their different stiffness. And then we have another boundary conditions that are used for the elements, such as beam and releases if you don't want to have any moments, or simulate simply supported beams, and so on. We have in this case also rigid links, as I mentioned or showed you in the model, to rigidly connect the superstructure with the bearings. This is more or less a diagram of how, in this case, the wizard generated the connection between the superstructure and the substructure. In this case, the program, what it did was it took two rigid links to the bottom portion of the girder, and then it connected the girder with the pier using an elastic link, in this case, which will be the bearing, and will simulate the bearing, and then a rigid link that is connecting the pier to those bearings. In this case, you can use this simulation to do that, or the program can actually do it automatically. We have different types of elastic links in the program, such as the general elastic link, where you can define the stiffness in each direction, translational and rotational. We also have a rigid elastic link, which is basically has a connecting two nodes with an infinite stiffness. We have also the tension only and compression only that behave in that way, and then we have the multilinear, which we can use to simulate the soil boundary conditions. Then we have general links, which is another classification of the links in the program, where we can define different types of devices, such as isolators, dampers, hysteretic systems, lead rubber bearing, friction pendulum system isolators, spring dashpot, or spring and dashpot together. You can define their properties in the program. As you see, the program has many options of simulating different types of elements of the bridge. So let me just go back to the model and perform the analysis of this bridge, and then go over the results. Here the program is telling me what, performing the static analysis, then it's gonna perform the moving load analysis. We also have this under the task pane. We can just click on the perform analysis tab, and the program will do this, and then here we have the different functions that we should go over. We have created this in the case that you guys perform different tasks frequently. You can create a text file that can redirect you to each one of the functions here. So let me just display the lane, and let's check the reactions. So here, as you can see, you can just click here and the program automatically redirects you to the reaction part. If you want, you can also perform the results, reactions, load combinations. Let me just define the load combination here. Under the concrete tab, the program can automatically generate the load combinations, strength 1, 2, service, and fatigue, and you can also add different load combinations for your particular project. In this case, let's check the reactions due to the self-weight of the structure. Here you can see the different reactions due to the self-weight. If you want to change it to pounds, you can change it to pounds. If you're okay with kibs, the program automatically updates the view. You can add a legend. You can see the legend here. Let's go back to the task pane and check the deformation. Let's do a displacement contour so you can see how the deformation is for this particular bridge. Here, let me just take out the values. This is for the self-weight, and this is the deformation due to the self-weight. Let me just fix the legend. You can fix the legend using this function here, and let's see what the legend shows us. If you want to have it in inches, you can just change the units, and the program automatically updates the units here. Let me just show you what the deformation due to the moving load is. Just check the maximum deformation due to the moving load, and you can see them here. Just show you the minimum also. Here you can see the deformed shape of the bridge. You can rotate the model 360 degrees without any problems, as you can see here. Let's also check the shear force and the bending moment. Let me check the bending moment due to the moving load, and let me just unselect the deformed portion, and let me do a solid diagram. Here you can see what the moment diagram, let me just change keep foot, is due to that particular moving load. You can also do for the self weight or any load combinations that you have here. As you can see here, let me do also a self weight, and you can also do it for the shear forces. So let me use select the shear component, which is FC, vertical direction, and here you can see the shear force generated due to that particular self weight. We have another option in the program that is called the moving load tracer. Here you can check the reaction or the location of the truck that generates the maximum reaction or force in a particular element or node. So let's say I want to check the reaction of the moving load due to these the reaction of this node due to the moving load. So let's say the maximum FC, what is the location of the truck that generates the maximum FC for this particular reaction? And here it is. The program shows me the location of the truck with the axles and also the load distribution, as you know, per the Ashtok truck. Here you have the different options for verifying the results. If you guys need these, we have it available. We created this for you so you can just go over it in your own time. Now going into the design itself, we have the design available in the program as per PSC or the steel as per Ashton RFD. We have created a design guide, which is something like this. It is also available, and where you want the PDF, we can also send it to you. That shows you each one of the different equations that the program uses for the design check. The procedure of generating the design in the program is very simple. After you have the wizard and you check all the results and the load combinations and so on, you can go into the design part of the program, and here you can define the materials that you're using. You can separate the materials as per the girders or slab. You can also define in these the materials for the rebars that you're using, and then you can obtain the different design tables. Let me just go over the design part, and in this case let's go into the PSC portion. So here you can define the design parameters, where you have in the PSC you have all the information for, or all the functions for defining, for doing the design check for the pre-stressed concrete superstructure in the program, or substructure. It's up to you. In this case, you have the different types of tendons, exposure factors for the crack width, flexural strength, corrosive conditions, the type of constructions that you have, and also here you can select the different parameters output for the design. Then you have the definition of the material, which is the one that I was showing you. You can access this one here, or you can also access this one through this function here. So you have the parameters, you have the materials here, and let me just assign the rebar information. I'm just gonna use grade 60 rebar, and for the slab I'm gonna use the also ASTM. and I'm just gonna define the rebar information here for this slab as well. You can modify it, and here you can see you can also use lightweight concrete if you want. Let me just close here. After that, you have the option of defining, this is an entire process, left to right, top to bottom. You can define the design position. In this case, I'm just gonna use the node or this element here. I'm just gonna select a small element, and you can select which component you want to check, which is the I node, the J node, shear or moment. Apply it, and here you can see a table. All the tables are generated here. You can see the table of which element is taken and which part of the element is taken into consideration. You can also do the output position, and I'm just gonna select the same element, and I'm gonna, for the output position, the program generates an entire Excel file that shows you all the calculations and everything I'm gonna show you now. So let me just do the moment shear strength for the I and J node, as you can see here, and then let me just perform the design. While the program performs the design check, we can obtain the different result tables as for the strength, the flexure, the shear, the stress, sectional principal stresses, shear strength, combined shear and torsion strength, and everything is provided to you in a table and also in a Excel format. In this Excel, you can see the equations that Ashto uses for the design. You can also check each one of the equations that the program uses for the check. Everything is very detailed, and also in the manual, the program that we have developed, the program tells you what parameters are taken and how it is doing the design check. So let's just go back to the design, and let's check the result tables. So let's say that you want to check the flexural strength for that particular element that we designed. Here you can have the positive negative moment check, whether it's okay or not. If it's not okay, the program tells you in red that it's not good, and you should just go back and check it. And then here, moment critical, MUI, the VMN, the ratios, and then from there you have an idea of how your bridge is behaving and whether or not it complies with the code. We also have an Excel report, which is the one that we use for the position for PSC output, in which the program generates an entire Excel report that you can use. I'm just gonna show you here. It's gonna be something like this one, in which the program tells you, the different equations. You can edit it. It's an Excel sheet that you can use as your own reference, or just to provide the report of your design. It's up to you. Or if somebody else is gonna check it, you can also do it through this Excel sheet. Alright. Here you can see the Excel sheet that I was telling you about. The program here gives you the definition of the properties of the sections that we are defining. Is in US units, and then the information of the tendons, also the different verifications that the program does, the different checks. So you can see the ASHTO clause, and also you can see the different verifications or checks. Flexural resistance, the program tells you whether it's okay or not. The shear resistance, also the program tells you whether it's okay or not. Torsion, also the program tells you whether it's complies with the code or it does not, as you can see here. So you can also have the tendon check for the stresses, whether they are okay or not, the principal stresses, and also the stresses for the shear. All this is an Excel sheet that you can use. You can edit it as however you want. You can save a copy, you can export, you can PDF it, whatever you want to do. You can do it using, and you can see here the equations. I mean, what's easier than that? We have put it in very well and very detailed manner so you can use it. Now going into the substructure design, we have in the program the substructure design function as per ASHTO LRFD. So we have implemented the different codes, previous codes and the recent ones, and in the program we can perform the design and we can also do a check. And the program gives us something like this with the diagrams, the rebar area recommended, also the check for the particular elements that we are designing. For, let's say, for the columns, we can also obtain the interaction diagrams and the recommendation of the rebars for the code. So let me just go over how the design can be done in the program. So we can first start by defining the strength reduction factors. You can basically update them as per ASHTO or define them you manually here. Those are the fees, so it's up to you how you want to use them. You can also define or modify the material properties as I did with the PSC. Is the same way of doing it. You can define the rebar materials that you want to use. You also have the option of limiting the maximum rebar ratio. In this case, you can define the raw or update it by the ASHTO. And then we have the option of using the beam section data for design. So here you can define the stirrup or the spirals depending on the type of section that you have. The covers and the rebar data for those particular designs, and then the program recommends you with that information the amount of rebar, the area of rebar that you can use to comply with the standards of the code. We also have the option of doing a checking similar to what we did for the PSC. You can tell the program the rebar information, and then from there the program tells you whether or not it complies with the ASHTO. You can do that for the checking, and then just to show you what the design looks like, the design looks like something like this. The program tells you the amount of rebar, and it does it as per different standards, as you can see, and also tells you the capacity, the bending, axial or shear capacity, also for the columns, as you can see here. And this is the diagram for the checking. Let me just go over it in the program to show you how this is done. So after you do the check for the PSC and the report, you can go over the, in this case, the design of the substructure. In order for you to perform the design, you just have to go to design tab, or you can jump into the tags pane, and we also generated these design functions for you. So let's say you want to define the materials. The program already has the materials for the girders or for the concrete. You can tell the program what to use. For the rebars as well, the rebar ratio, you can define it here. The raw, as I said. The strength reduction factors, you can also do them here. 0.75, 0.9 is up to you, updated by the code, and then click OK. Material design code, we have different design codes, ASHTO, Canadian, and you can apply the seismic provisions. Perfect. Then we have the beam section data for design. Here you can design or tell the program what the stirrup information, the cover information is, and then from there the program takes that information and generates a design. in which the program recommends you the amount of rebar or the area of rebar to use for that particular element. Then we have the column section data for design, in which you can also define the cover thickness and the ties or spirals, and then from there the program provides you the area of rebar to use for that particular column. Let's just do the column design just to show you, and then we're gonna go over the checking part. So after you define the beam and column section data for design, you can just click the column design part. In this case, I am selecting the columns, and then the program from there, what it's gonna do is it's gonna give me an area of rebar to use. It first tells me whether or not the section complies with the code. You can see a summary here, and then you can select by member and connect it to the model. Connect to model view and select which member you're designing. So in this case, let's say I'm checking this one. You can hit the graphic part, and then the program is gonna show you something like this. It's gonna give you the total area of rebar as a recommendation, the thickness, the DT cover, and then it's gonna give you the axial capacity and moment capacity due to the particular rebar information, the load information, and the load combination that creates the maximum effect for that particular check. Also, you can get the interaction diagram from the section, and also a shear force capacity check with those load combinations that you define. You can add the seismic forces. You can add any type of force that you need to in the load combination so that the program can do the design for it. You can also obtain a detail report, which is, if you hit detail, the program gives you a very detailed report with the section properties, the load combinations used, the forces of the load combinations, and then the different checks and design parts that it does. The phi 0.9, the equations used for design, the moment, the shear, depending on the type of element that you're using. You can do the same thing for the girders. Let me just select the girder, the pier caps, so that we can design the girders as well. You can do the same for the concrete code design, beam design, and then here the program tells me whether or not it complies, it's okay or not. If it's not okay, the program will tell me in red and tell me what part is not okay. And let me just select one of them to show you. Here the program tells you the area of rebar to use, and also the stirrups to use, and the capacity of shear capacity, moment capacity, and the torsion ratios. That is for the design. We can also do the checking, as I mentioned. So for the checking, you have the options here, which are the section beam section data for checking, or the column section data for checking. So let's say I want to assign number 3 at let's say every feet, or every 6 inches, and I want to assign 20 number 8 rebars for that particular section. So here the program draws me the diagram. I can just add or replace it. Here you can see a 0. It was an X before because there was nothing added to it. Now it's a 0, which tells me that this information has been added. And then from there I can go and press the check button, which is the concrete code check, column checking, and then with that information that I assigned to that particular section, the program is going to do the code check and tell me how is the column behaving. In this case it says it's okay, and let's check let's do the same column that I did before. Here we can see that with that particular reinforcement, we have a row of 0.01, it's like about 1% rebar, and then we have the rebar information and the axial capacity and the moment capacity with that particular reinforcement. We can also have the, as I mentioned, the interaction diagram, the shear check, summary, and the detail of the check in this case. Here we have all the information, the loading, and the checks that the program did, whether or not it complies with the code. This is how you can define you can perform the substructure design in the program using the different functions that are available in MyDaCivil. We went over the superstructure and the substructure. In this case, we have combined them to create a more realistic behavior. As you saw, I didn't have to switch between programs to perform the design of each one separately or to transfer the load and analyze them separately. This is a more or less simplified method of performing it, since we don't have the soil properties we were gonna go over in the next session. But in this case, we didn't separate the superstructure from the substructure. We did all the analysis and design using the same platform without having to switch around or transfer information, or just simply by the fact that you're using another platform generates easily, you can easily generate mistakes, or you can easily just take you a longer time on the analysis. Everything here is defined or assigned in the model. Everything is assigned in this particular work tree. So here you can see the different parts of the model that are assigned. This is basically how you can perform the entire design of the bridge. In this case, as I mentioned, we don't have the soil, but we will in the next session, so keep that in mind. For the next session, we're gonna have the soil structure interaction, and this will have the different properties or functions that we have for the soil spring supports. As you can see here, we can do for integral bridges. You can see the behavior of the bridge using that particular soil, which is very important as well. And this will be it. Thank you all for your attention. If you guys have any questions, please submit your queries into globalsupport@midasuser.com. This is our platform for the technical support around the globe, so yes, just please use it. And thank you all for your attention, and see you in the next session for solid structure interaction. Thank you very much.